Hello. In this video, we are trying to analyze the hydrogen NMR, or what's called the H1 NMR of two compounds. One of them is the ethyl acetate and the other one is the aspirin. We try to give more detail to the ethyl acetate. Sorry for that. We try to give detail about the ethyl acetate since it's a simpler one so that the audience can understand the concepts behind this. And then we can go over faster on the aspirin. So in this slide, as you can see, is that we have the ethyl acetate, the H1 or the proton NMR of the ethyl acetate. And one thing is that how can you know whether it is a proton NMR or the carbon NMR is by looking at the axis of the NMR. We can see that it is from 0 to 5. So most of the time, or as we have that, is the H1 NMR is ranging from the 0 to 12 ppm, while the carbon NMR ranges from 0 to almost 200 ppm. So here we have the proton NMR. So the first thing that we start with is the number of signals. How can we know that? How many signals that we have on the NMR? So here we see that we have 3 signals. This is one, like this whole collective thing we call one signal. This is the second signal, and this is the third signal. So here we can see that we have 3 signals. How can we tell that we have 3 signals is by looking at the hydrogen and the surrounding of the hydrogen so that we can tell how many we have. So the first thing is that this group of hydrogen are all bonded to the same carbon, so they are equivalent hydrogen. So this is one signal. This group of hydrogen is bonded to a carbon atom, so this is the second group of the hydrogen. This one is also bonded to another carbon. So this tells that we have 3 signals, and as we showed here, we have 3 signals of the hydrogens. So the number of signals can be detected by finding out how many equivalent hydrogens we have, how many different equivalent group of hydrogen we have. Here we have 3 different groups of equivalent hydrogen. The second thing that we try to understand is the position of the signal, like why we have the signal here, why we have the other one here, and the other one is further downfield. So one point that we have to make is that as we go further here, we call this downfield, like going down. And also we mostly relate this to deshielding, and we talk about both of them. It's just a convention that we call this a downfield. Sorry again for my glitch. It's like just don't know how to. Yeah. So let's identify which signal belongs to the group of equivalent hydrogen. So the first signal that we called here is near the 0, or it's like the upfield. So we look for the group of hydrogen that's bonded to a carbon that's further away from an electronegative atom. So here we have, so sorry for my, it's like the cursor is, I think that's, so for the first one that we have here is that how can we tell whether this one belongs to this or this or this? So we look at the environment of the hydrogen and see whether if they are further away or very close to a very electronegative atom or group. So by looking at the group of the equivalent hydrogen, we can see that this one this group here, this, like, using another color, sorry, not yellow, let's use blue. Yeah, this group here, this group is further away from the electronegative atom, so that it's most probably will be found here because it's upfilled. It's the least deshielded group, so we assume that it's here. The second one that we have it here is that whether it is this one or this group, as we can see, this one, this group that we have here is bonded to a carbon atom and then to another carbon atom. However, this one is bonded to a carbon atom and then to an oxygen atom. So this group of three would tell us that this is most probably for the signal two, for the second signal. This belongs to this signal. And the one in the last one using a different color like green is that, which is the most downfield or deshielded one, is this group here that's bonded to the oxygen atom and then bonded to a carbon and an oxygen double, which is like directly bonded to a carboxylic acid group. So the one that's further downfield is the one that's most deshielded. So I clear all the drawing. So we figure out that just by color. Let's redo it again. This belong to this. This belong to this. And this one belong to this one. So we talk about these two. Let's go to the third one. The integration of the signal. The integration of the signal basically tells you how many hydrogen you have there. So here we have 3, and it basically tells you that you have 3 hydrogen here. Here you have 3 again, and it basically tells you that this signal belongs to the number, to a total number of 3 hydrogens. Here we have 2, so this basically tells you that this belongs to this one. Yeah, that's all the thing about the integration. It's nothing very like confusing. Usually we use computer to do the things about that. And let's do the last one for the spin-spin coupling. So as we can see here that this belongs to here. So how this splitting happen, like this coupling or a splitting pattern here, that happens here, so that we want to look at this. So the thing that we have here is that we have 3 equivalent hydrogen bonded to a carbon, and this carbon here bonded to another carbon, which is bonded to 2 equivalent hydrogen. So we use the n+1 rule here to tell that. So we have 2 hydrogen here for the n, so 2 plus 1 is equal to 3. So we have 3 splitting here, or for the spin that we talk about here. For this one, which belongs to here, we don't have any other carbon that's bonded to hydrogen, so this is the n here would be like n+1 again. Here the n is 0, so 0 plus 1 would be 1. So that's for that one as well. And for the last one, that we have 4, a total of 4, like a spine things. Yeah. So how do we get this 4? This one and belong to this group of carbon. On the left side, there is no. On the left side, there is no carbon bonded to hydrogen, but on the right we have 3 carbons. So using the n+1 rule, 3 plus 1 would be 4, which is we have here 4 splits into 4. Yeah, so I think this is all about the ethyl acetate that we gave in our detail about how to do the things about it. And for the second one that I want to go to, but how to stop annotate, this is difficult. Okay. Yeah, so going here. So the second one is about the aspirin, how to do the analysis of the aspirin. Again, that we have, let's annotate. So I think this is not a very complete picture of the NMR, but let's do a very rough estimate of the things that we have. Here we have a carbon that's bound to 3 hydrogen. Here we have a different carbon. This is the first set of the hydrogen. This is the second one. This is the third one. This is the fourth, and this is the fifth. And we have another hydrogen here, which is like part of the carboxylic acid. So as we can see that we have 5 signal, 1, 2, 3, 4, and 5. So this tells us that this is, although I think we should have one more signal here. I just confused about this. Let's, for the sake of the explanation, let's assume that we have only 5 here. And similar to the previous explanation is that this time we have a benzene ring. So a benzene ring, that's very important part of this aspirin, tells us that the group of the equivalent hydrogen would mostly be found around 6.5 or 7 to almost 8.5. So anytime you see the shift around 8 ppm, this tells you that there is a benzene or an aromatic ring. And for the last one that we have here, it's around like between 10 to 12, around 11. This tells you about this group of what we call hydrogen here, which is bounded to an ester. Like this one is the most deshielded one, and so this is like further downfield. Similar to the other explanation that we made, why we have this amount of signal is because we have 5 different 1, 2, 3, 4, 5 different equivalent group of hydrogen. Why we have this one is like further downfield or deshielded is because it's like bonded to an ester or a carboxylic acid. Like that's why I'm a little bit confused about whether it's belong to this one or this one, but yeah, it's clear that it's not this one because this one is yeah, it should be this one because that's the most deshielded one. And the other things is that since we have almost three groups of the, yeah, that's why I said there must be something missing here, because we have one group of hydrogen here. This is the second group. And I think this is the 3 and 4th group, or only the 3rd group there. So this tells you why we have the number of the signal. Again, using the n+1 rule, we can tell the splitting pattern of this, but since they are not very clear here, it's like very difficult to tell. Also, again, using the computer integration, we can talk about how many hydrogen is bonded there. And lastly, I think there's nothing else to say about this. Yeah, I think that's all we can say about this one. Thank you for watching.